welcome to the intermolecular interactions video. These intermolecular interactions that we're going to talk about are going to be very important in terms of solubility and boiling point as we move through the course. So not only solubility and boiling point, but also density, solid, liquid, gas, melting points, all of those things are affected by these attractions between separate molecules. The four primary types are dispersion forces, which are also called London dispersion forces and or van der Waals forces. Those are the weakest, but strength in numbers, so there's a lot of those. Second is dipole-dipole, and this is where we have a molecule that has two atoms next to each other that have a difference in electronegativity. Third is hydrogen bonding, and this is a special case, and we will talk about that in a little more detail, but as we move down this list, we're getting stronger and stronger. So hydrogen bonds are quite strong. And finally, we have ionic bonding. And this is where we have a full out positive charge and a full out negative charge on atoms. And then they interact in that way. The first of these is dispersion forces. These are nonpolar molecules that typically have carbon and hydrogen only, but they still do have an attractive force between them, even though the electrons and the protons and the neutrons are all kind of evenly spread out around the molecule. It's a transient dipole, meaning that it's temporary, and it's called London dispersion forces. So if this molecule here, for whatever reason, becomes partially negative on this side of the molecule, because it's so close in distance to this molecule, it induces this one to have a partial positive on this side. So basically what happens is a partial negative has more electrons on this side of the molecule. And then if it comes in contact with this molecule, it'll push the electrons down here to have most of the electron density over here. And so because of that shift in electron density within the molecule, we end up with an attractive force between the two. So what we should know about dispersion forces are that it is a fleeting attraction, it is weak, but that there is a strength in numbers. And if we think about London dispersion forces, we can think about as we increase the surface area, we end up with more temporary dipole attractions. So the larger the surface area, the more attraction we have. And so if you think about the feet of a gecko, they have flexible hairs on their feet to maximize that surface contact, to allow them to kind of defy gravity and support their weight. The other thing in terms of surface area, so the more intermolecular forces is directly related to a higher boiling point. This is a relationship that you need to think about all the way through all of organic chemistry. Increased intermolecular forces means increased boiling point. So with that said, let's see if we can decide which one of these carbon molecules has the highest boiling point. The first one here is 4 carbons, 5 carbons, and 6 carbons long. So if you want to just take a second and think about which one of these do you think would have a higher boiling point, maybe pause the video. And the answer is butane with only 4 has a boiling point around 0 degrees Celsius. Pentane with 5 carbons has a boiling point of 36, and hexane has a boiling point of 69. So you can see that just by increasing the size of the molecule, we end up increasing the surface area, and then we end up increasing the boiling point. Now, what about this? We haven't talked about this. Okay, so we have 6 carbons in all 3 of these molecules. This is a straight chain here on the left, and then we have 1 branch, and over here we have 2 branches all the way to the right. So which one of these do you think would have the highest boiling point? Pause the video. Well, if you said that the straight chain would have the highest boiling point, you are correct. And the reason for that is increased surface area. A bunch of years ago, I had a student who described this phenomena as stackability. So the long linear molecule is like a piece of wood without any branches. And you can stack a whole bunch of these much tighter, and you can pack it much more evenly, and you get a nice straight pile of the highest interaction, the highest surface area touching the one next to it. Whereas if you have a branch, right, sticking out of the molecule, then that makes it a little bit harder to pack in that wood pile. And so that's also going to minimize the amount of intermolecular interactions, and it's going to decrease the surface area and therefore decrease the amount of intermolecular interactions. And if you have a piece of wood with a branch on each side, you can imagine that'd be like trying to pack a rubber ball in the middle of a pile of wood. And of course, that circular structure is not going to pack nicely. So you can see that we have the highest intermolecular interactions here, followed by this one with one branch, and followed then in the end comes the one with multiple branches. So increased branching actually decreases the surface area and makes for less intermolecular interactions. The second on our list is dipole-dipole interactions. And this is a molecule that has two atoms next to each other in the molecule that have different electronegativities. And so this now is not a temporary one, this is a permanent one. And so if we look at acetone above, we see that that oxygen at the top of acetone is partially negative, and then the carbon next door is partially positive. That partially negative oxygen is going to line up with and interact with partial positive carbon next door. And likewise, this partial negative is going to interact with this partial positive. And so we end up with a stronger force because it's not temporary, and it's based on the electronegativity differences in our molecules. And if you look down below, you can see the difference between isobutylene and acetone. So acetone, because of that partial negative oxygen and partial positive carbon, would have dipole-dipole interactions. So we see a boiling point of 53 degrees Celsius. Whereas if we have isobutylene, we still have that double bond here, but we do not have any difference in electronegativity. So that boiling point is in the negatives. So it turns out that isobutylene is less polar and therefore has a weaker dipole-dipole interaction and therefore has a lower boiling point. Where acetone has this dipole-dipole interaction for sure, so that increases the boiling point. Then we have hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interaction. And what we want to think about in this case is that we need the elements nitrogen, oxygen, or fluorine, NOF. So if we do not have nitrogen, oxygen, or fluorine in our molecule, there's no way we can have hydrogen bonding. And so hydrogen bonding is an attractive force between a hydrogen that is on any one of these, right? So a hydrogen that's on a nitrogen, a hydrogen that's on an oxygen, or a hydrogen that's on a fluorine. So it's an attractive force between that hydrogen that's on the oxygen and the lone pair of another oxygen. And so and it only happens with NOF. And so this is a very strong intermolecular interaction. It's very, very important in biology and in organic chemistry. So if you think about water, H2O, we have two hydrogens and two lone pairs. So the hydrogen that's on one of those water molecules is going to have a very strong interaction with the lone pair that's on another molecule of water. And so this is why the boiling point of water is 100 degrees C, because water can actually form a network. Second, if we think about in ammonia, we have the hydrogen that's attached to the nitrogen, and then we have this hydrogen bond that happens with the lone pair of the nitrogen next door. So this is a really neat force. It's definitely crucial in organic chemistry, but remember, we always need NOF. So only when hydrogen shares its electrons with a very electronegative atom like NOF will it carry that large partial positive charge. So the large partial positive charge on the hydrogen can attract the partial negative charges of other molecules, specifically of lone pairs, as you see here. So it doesn't just happen with water and ammonia. So we can get this hydrogen bond interaction between the hydrogen that's on the oxygen and the lone pair that's on another molecule's oxygen. So as I told you, hydrogen bonding is the strongest of the three intermolecular interactions. It turns out it's still about 20 times weaker than a covalent bond. So we're not talking about covalent bonds here in any of these cases. So 20 times weaker than a covalent bond. Your solvents that engage in hydrogen bonding are called protic solvents. And there is an example here, which is acetic acid. Solvents that do not have the capability of hydrogen bonding are considered to be aprotic. And so we have ethers, and this one is dimethyl sulfoxide. You can pause the video, but what I'd like you to do is rank the following three amines for their boiling point. So it turns out propylamine over here on the right has the highest boiling point because it has two hydrogens that are capable of hydrogen bonding. Ethylmethylamine comes in second at 37 degrees because it has a single hydrogen, 2 hydrogen bonds. Now, if we look over here at triethylamine, there's no hydrogens on that nitrogen at all. So this molecule cannot hydrogen bond, which is why its boiling point is so much lower. So an increase in the amount of hydrogen bonding will increase the boiling point. And finally, what does this matter in real life besides organic chemistry? It turns out that the alpha helices of proteins and the double helix of DNA are all held together by hydrogen bonds. With the protein alpha helices, we have the backbone of the protein interacting with itself in terms of hydrogen bonding, and in DNA. Remember, we have GACT. Between G and A, there's 3, and then between T and C, there's 2. And so these interactions that we've been talking about in biology for years are actually hydrogen bonds. So this is important in solubility too. So as you've learned in general chemistry and maybe even in high school, likes dissolve likes. And so the way that we want to think about this is polar molecules will be soluble in polar molecules. And by polar molecules, I'm talking about molecules that are capable of hydrogen bonding and or have strong dipole-dipole. And nonpolar compounds typically are going to mix well with other nonpolar compounds. Compounds that don't have any hydrogen bonding and don't have any dipole-dipole are going to be soluble in each other. So likes dissolve like is the bottom line there. We know that compounds don't mix that are not alike. For example, oil, which is a very nonpolar compound, and water, which is a very polar compound with that hydrogen bonding, but those two compounds do not mix. And so if you think about how are you supposed to get dirt off of your hand if it's oily, right? Water won't wash it off. Have you ever gotten paint on your hand or glue on your hand and you could not get it off with water? That's because water will not dissolve the oil on your hand. And so we can't just wash it off with water. We have to use soap. We have to use detergent. And what soap does is it has a polar head group. So that is going to like the water, right? And then it has this non-polar tail. And so that non-polar tail is going to attract and dissolve the grease or the paint or the dirt that's on our skin or on our clothes. And so this is called a surfactant. It has a hydrophobic group and a hydrophilic group. So hydrophobic does not like water. Hydrophilic loves water. It has both. So the soap is soluble in water, but it also will pick up the big hydrophobic dirt. And just to take it a step further, what happens is the soap molecules organize themselves into micelles in the water. So these are the polar head groups. So here's where the water all is touching. And then the dirt is inside next to all these hydrophobic tails with all those non-polar groups. So who'd have thought we would learn about washing our hands, yet again, COVID-19, in organic chemistry based on solubility of organic compounds. So as crazy as organic chemistry may be, we can apply it often to our daily life. There you have it, intermolecular interactions as it relates to solubility and boiling point.